So the whole of real analysis is about studying the real numbers. This video is going to be absolutely crucial because in this video we're going to look at the foundational properties of the real numbers, and the whole of the rest of real analysis is the consequences of the properties that we're going to discuss in this video. So this is absolutely crucial. So where do the real numbers come from? What is the point of them? Why did we try to create them? Well, the whole motivation is to try and create a mathematical model of one-dimensional reality, the one-dimensional continuum. This is why we talk about the real line, because the one-dimensional line is the whole purpose of the real numbers. It's what they were created to try and model. So let's imagine that we're going to try and do this. So we want to ideally give every single point on this line a name. So to start with, let's just start by giving one of the points on the line a name. So we'll go for this point here, and we'll start by calling that the point 0. So let's now continue on giving more points names. So I know I've progressed the picture forward quite a bit, but imagine that only this point is named at the moment. Then we can go to another point, and we'll go to the right of 0, so we'll go to this point, and we might name that 1. Now, of course, these symbols we're using, they come from the rational number system. The previous video that I did in this playlist on real analysis was on ordered fields, where we discussed the rational numbers and the order that you can put on them such that it obeys the axioms of an ordered field. And you know from years of doing naive maths in school that the rational numbers actually very nicely does a model, if you like, of the one-dimensional continuum. Not a perfect model, and that's what we're going to see, that the rational numbers has holes in it, but it very nicely can be laid down on a line, and the algebraic properties that are defined on the rational numbers behave very nicely geometrically if you do that. So that, of course, is the reason we're doing this. So continuing on, so we've got this point that we've named 0, we've got another point that we've named 1, and of course we've put 1 to the right of 0 rather than to the left of 0, because we know that it's going to behave nicer if we do that, because we know where we're going. We know the answer, so we are kind of cheating here. And then we can name another point. So now what I want you to do is look at this gap, this geometrical gap between 0 and 1, and take the same gap now forward again to go to where we're going to call the next point the number 2, and so on. Then you can go forward again by that same length on your one-dimensional line, and then you'll call that point 3, and you can continue going on, and then we're going to use all the symbols that we have for the integers labeling up points along here. And similarly, the additive inverse of 1 in our abstract number system, our abstract set of symbols, we're going to call that the point to the left of 0 that is the same distance, the same geometric gap here that is between 0 and 1 here. So you're going to space them all evenly out. And all these points now have names. Of course, we're not done. Of course, there's loads of gaps here, loads of points in between that haven't got names, but we have at least made a start at naming some of the points on our one-dimensional line. And you can see that adding these symbols together in our abstract notion of what it means to add integers together has a geometrical meaning because of the fact that we have spaced the points evenly. We've kept the same distance between them. If you'd not kept the same distance between them, if you just named these points up randomly, the algebraic structure that we have defined on these symbols wouldn't then have any geometric meaning. So that's the reason we're doing it nicely like this, because then all of the algebraic properties and the order properties that we now know can be put on the rational numbers is going to have a geometrical meaning on our one-dimensional continuum, and of course that's very helpful in physics. I want to highlight this point about the geometrical meaning of addition and indeed multiplication if you space these numbers uniformly along this line, because this is really important. So if we, for instance, consider 2 plus 3, this has an abstract meaning in the abstract algebraic structure of the integers, but now, because we have spaced the numbers uniformly on this line, it has a geometrical meaning as well. So the geometrical meaning is, consider the arrow that you have to create to go to each of the numbers that you want to add together, and then the answer of what the two added together is going to be equal to is it's whatever the two arrows put end to end arrive at, whichever number they arrive at. So here is the arrow for 2, here is the arrow for 3. If you put those two arrows together, you'll get this big green arrow here, which goes to 5, which then is the answer in the abstract algebraic structure as well. And this works for the negative numbers as well. Say you want to add 2 to negative 1. In the case of the negative numbers, the arrows are pointing in the opposite direction because you're always considering the arrow from the origin point, the 0 point. So the negative numbers, it's going to be a opposite directioned arrow. So if you are doing 2 plus 1, you take the green arrow for 2 and then you put on this blue arrow for negative 1, and that will take us back to 1 here. So the answer is 1, which of course is again the answer in the abstract algebraic structure. So important, when you use these numbers like this, you put them uniformly along a line like this, their addition rule has a geometrical meaning. And it's the same for multiplication, as we'll show now. So the geometric meaning of multiplication then, let's consider an example. So let's consider 2 times 3. What's the geometrical meaning of this? So when you multiply one number by another number, the geometric meaning of that is you want to scale this number up by the amount that you would have to scale 1 up to get to this second number here. So let me explain this more. So here we have our number 3. It is this arrow here. You want to compare that arrow to the size of the arrow going to 1. So in red here, this is the arrow going to 1. So you can see how much bigger the arrow going to 3 is. When you multiply the arrow going to 2, or when you multiply 2 by 3, the geometrical meaning of that is that we want to scale this arrow here, this 2 arrow, up by the same amount that you would have to scale the 1 arrow up to get to the 3 arrow. So you want to stretch this arrow by 3 times to make it 3. So you're now, if you're going to multiply the 2 arrow by 3, you want to stretch that by 3 times, just as you would stretch the 1 arrow by 3 times to get to 3. So of course that's going to give this answer up here. This is this arrow stretched the same amount as this arrow has been stretched to get to here. So it's stretching. That's the geometrical meaning of multiplication. And of course this arrow goes to 6, and that's the answer in the abstract algebraic structure as well. Multiplying by negative numbers also obeys this stretching. So of course the arrows going to the negative numbers are pointing the opposite direction, so their ratio to the 1 arrow is actually not just stretching but also flipping around the other way. So, you know, to get to the negative 2 arrow, for instance, from the 1 arrow, you have to not only stretch it by a factor of 2, stretch it out twice, but you also have to flip it round. And that meaning pans out. So if we consider 2 times negative 2, what we want to do is we want to take this 2 arrow, in order to multiply it by negative 2, we want to stretch it and rotate it by the same amount as you would have to stretch the 1 arrow to get to negative 2. And of course that's going to again mean rotating it around so it faces the other way and stretching it by a factor of 2, so it will arrive at negative 4 over here, which is of course again the answer in the abstract algebra. So both addition and multiplication have this geometric meaning when you space the numbers out uniformly on a line like this, and it becomes obvious that from the geometry that the familiar properties that the addition and the multiplication laws obey in abstract field theory, so things like associativity, commutativity, distributivity, all of these rules, it becomes intuitively obvious why they're true when you look at this geometrical meaning of them like this. It also becomes intuitively obvious why the properties of the ordered field hold true. So those two axioms that we looked at in the previous video, again, they have incredibly intuitively obvious geometrical meanings as to why they are true. Now, with this geometric meaning of multiplication, it's incredibly obvious then where all the other rational numbers have to go on our one-dimensional line in order for the geometrical meaning of addition and multiplication to hold up. So for instance, if you consider a half, where's a half going to go on our one-dimensional line? Well, we know that a half times 2 has to equal 1. So it's going to have to be the place on this line where the arrow from 0 is such that if you double it, you end up at 1. So it's going to have to therefore be halfway between 0 and 1 on here. And equivalently, you can work out all the other fractions exactly where they have to be on our one-dimensional continuum. So where have we actually got to now? Because it's quite easy to lose sight of what we're actually trying to do here. So what I have shown you is that when we are trying to model one-dimensional continuum, one-dimensional reality, it is possible to model it with the rational numbers. It's possible to put the rational numbers along the one-dimensional line, and it's possible to do it in such a way that addition and multiplication have incredible geometric meanings. The order property obviously has an incredible geometric meaning, and indeed the ordered field properties also have an incredible geometric meaning. Now, this is a reasonably good model of the one-dimensional continuum because, after all, rationals get smaller and smaller and smaller. You can take a smaller n, you can look at a third, you can look at a quarter, you can look at a fifth, you can look at a sixth. So it looks as though you're going to get a huge number of points on our one-dimensional continuum hit by this model. So maybe this is it. Maybe this is good enough to model the one-dimensional continuum. And it is true, it's reasonably good. However, there is a fatal flaw in it, and we'll discuss that flaw now. And that's the flaw that leads you to need the real numbers, something bigger than the rationals, to model the one-dimensional continuum. So the easiest way to see the fatal flaw with the rational numbers as a model for the one-dimensional continuum is with Pythagoras' theorem and the square root of 2. So just a reminder then of why Pythagoras' theorem is true. So if you take a right-angled triangle, so this is our triangle here, and it has sides A here, B here, and C here. What you can do is copy this triangle so that you've got 4 of them, 4 copies of it, and then you can rotate it. So if you rotate it round 90 degrees this way and then put it up here, so now side A is here, side B is here, and side C is here, and then you take another one, rotate it around again another 90 degrees, and then put it like so, and then the final one, rotate it final 90 degrees and put it like this, then you can make a square here where the sides of the square are A plus B, and then inside there is this smaller square where the sides of that are C and C. So the area of this larger square is going to be A plus B squared. The area of the smaller square is going to be C squared, but we also know what the area of the triangles are going to be equal to. They are going to be A times B divided by 2. So the area of all 4 triangles together is 4 times that, which is 2 times AB. So the area inside this box can be worked out 2 ways. Either it's equal to the area of this box plus the area of the 4 triangles, which is C squared plus 2AB, or it's equal to A plus B squared, which is the side of the larger square times itself. So we get this equation here, C squared plus 2AB is equal to A plus B squared. If you expand this, it makes A squared plus B squared plus 2AB. The 2AB's cancel from both sides, and you then end up with that C squared is equal to A squared plus B squared, which is Pythagoras' theorem. So now what we can do is we can consider making a little triangle where the sides of the triangle are going to be equal to the length of the arrow from 0 to 1. So here we have our little triangle here, and then by Pythagoras' theorem, the length of the hypotenuse of this triangle is going to be equal to root 2, where I'm just using this symbol root 2 to mean some length, which we could call L, which is going to obey the property that L squared is equal to 2. And of course, we'll use the symbol that we're used to using from school level maths, the square root of 2 for that. Now, there is no such number, unfortunately, in the rational number system. There is nothing that, if you square it, will equal 2. And the proof of that is quite simple. We'll do it down here. So let's suppose let's suppose there is some rational, so something of the form a over b, where a and b are both integers, that if you square it is equal to 2. Now, when I choose this rational here, I'm going to make sure that there are no common factors in the numerator and the denominator. So of course there are loads of fractions that are all equivalent in the rational numbers. The rational number system is made up of equivalence classes of fractions that are all equal to the same thing and are just degenerate versions of each other. They're versions that have the same factor in both the numerator and the denominator. So I'm going to make sure that when I pick the representative from the equivalence class that I'm going to use here, I'm going to make sure that there are no common factors in the numerator and the denominator. So if there were common factors, I can cancel it down. So let's say this fraction was a third. Another equivalent form of that would be 6 over 18. So 6 over 18 is the same fraction as a third. It's just a degenerate version of it, and it's the version of it that has got common factors in the numerator and the denominator. Indeed, 6 is a common factor. So in the numerator you've got 6, and in the denominator 18 is 6 times 3. So you've got a 6 there. So I'm going to make sure that you've cancelled that common factor. So you cancel out the 6 and you get back to a third. So we've chosen the usual representative that we like to use, the one that doesn't have degenerate factors in both the numerator and the denominator. So we're going to assume then that there is no common factor in both the numerator and the denominator here. And we're going to arrive at a contradiction. So if you multiply this out, you get that a squared over b squared is equal to 2 times both sides by b squared, so you get a squared is equal to 2 times b squared. Now what that implies is that a squared must be an even number, because the thing on this side is going to be an even number. Whatever b is, it is some integer. Square it, you still end up with an integer. Multiply that by 2, you then end up with an even integer. So that implies a squared is even. Now that in turn implies that a is even, because when you square an odd number, you always end up with another odd number back. When you square an even number, you end up with another even number back. So if you square something and get an even number, it implies that the thing you squared was an even number. So that means that a can be written as 2 times some other number because it's an even number. Now put that back in place of a, so 2 times x over b, square all of this, that's equal to 2. Multiply this out, you get that 4x squared is equal to 2 times b squared. Cancel the 2 and you then get that 2x squared is equal to b squared. That's a problem because that then implies the same thing about b. It implies that b squared is even because it's 2 times x, and again x was some integer here. When we wrote a as equal to 2x, we were just saying a is an even integer, so it can be written as 2 times some other integer, so x is an integer as well. So x squared is an integer, so 2 times x squared is some even integer, so that implies that b squared is an even integer. And again, same argument now, if you square an integer to get an even integer back again, that integer you had squared will be even. So that then proves that b is even as well, but that's a contradiction because we said at the start that we were choosing a and b, this representative from the equivalence class, such that there were no common factors, but now we've proven that both of them are going to be even, so there was a common factor, a factor of 2 in both of them. So that's a contradiction. So there can be no rational that squares to give 2. So this is a flaw. We were using the rational numbers as our model for the one-dimensional continuum, but I have shown you now that there is a point that is around here on our one-dimensional continuum, the length of this triangle here, that is not represented by any symbol in our mathematical structure. There's a hole in this mathematical representation of the one-dimensional continuum. This is not big enough, this is not good enough to represent the one-dimensional continuum, and we need to solve this problem, and that's where the real numbers are going to come from. To stress the importance of this again, think of the physicists and the engineers. You are telling them that the answer to what the length of this triangle is not represented by any value within your model for one-dimensional reality. So clearly this model is not good enough. They're not going to be happy with you with this model. So we need a better model, and that indeed is where the real numbers are going to come from. So how do you create or define or characterize this larger structure then that we're trying to get at? Well, in order to do this, we need to introduce a new concept, and that new concept is the least upper bound, or LUB, or LUB, or Supremum. So this is a concept that comes about because we now have the order properties defined on the rational numbers. So it's an extension of the concept of the maximum element within a set. So let's illustrate this with some examples. So if we take this set, which is a subset of the rational numbers, so it's all the elements between 0 and 3, including the elements 0 and 3. So when you have square brackets like this for an interval, it means including the boundary points, so including 0 and 3. So because we've defined the order property on the rational numbers, we can then talk about the maximum element within this set, which is the biggest element within this set. And this set does contain a biggest element. It contains the element 3, which is greater than or equal to every other element within the set. So this set has a maximum, and that element is 3. If you now consider this set instead, which again is the interval from 0 to 3, this time, however, it includes 0, but it doesn't include the point 3, so it's all the rationals lower than 3, and of course you can get infinitesimally close to 3 within the rational numbers, but it doesn't actually include the element 3 itself. Now this set does not have a maximum element because every rational in here, you can always find another rational that's slightly closer to 3. So if you think you've found a maximum within here, all you need to do is go halfway between that rational and 3, and then you'll have another rational there, which is bigger than it, and is still within this because it's less than 3. So there is no maximal element in this set. Instead, we have this concept of the supremum, which we abbreviate to sup, or the least upper bound of this set instead, and that is going to be equal to 3. And the formal definition of what this means is that it is an element that is an upper bound for the set. So the definition of an upper bound is an element that's greater than or equal to all elements of the set. So for instance, 5 is an upper bound of this set because it's bigger than all the elements within the set, bigger than or equal to all the elements in the set. 6 is also an upper bound. Anything that's greater than or equal to every element within a set is an upper bound for the set. The concept of a least upper bound is then the smallest of all of the upper bounds. So it's got to be an upper bound itself, so greater than or equal to all the elements of the set, but it also has to be the case that if you take any element smaller than that element, it has to not be an upper bound. Hence why it's the smallest of the upper bounds. So you cannot have a number that's smaller than it that is still an upper bound. So in the case of this set, 3 is the least upper bound of that set because it's an upper bound, it's greater than or equal to all the elements of this set, and there's no smaller upper bound. So if you go any smaller than 3, that number now is not going to be an upper bound. It's going to be inside this set, and indeed there's going to be another number inside the set that is bigger than it, and therefore it's not an upper bound. So if you take, for instance, 2.9, that's a number smaller than 3. That's not going to be an upper bound because 2.95 is another element of this set that is greater than it. So it destroys the definition of the upper bound. It cannot be an upper bound in that case. In the case of sets that actually do have a maximum, like this set up here, the least upper bound for that set is the same as the maximum. 3 is still the least upper bound of this set because it's greater than or equal to every element in the set, which is all it needs to be an upper bound. So you might think, but 3 is actually in the set, so how can it be an upper bound? Well, it can be because the definition isn't that it needs to be greater than all the elements within the set, it's that it needs to be greater than or equal to all the elements of the set. So the fact that it's in the set doesn't matter because it can be equal to that final maximal element within the set. So it is going to be an upper bound, and indeed it's still the least of them all because any smaller number is not going to be an upper bound. But this concept of least upper bound generalizes this concept of maximum. It means that for sets that don't actually have a maximal element, you can still talk about what the boundary of that set is, what the edge of that set is. Now, why are we suddenly talking about this? Well, the reason is that this concept of least upper bound becomes really helpful in specifying or defining or characterizing a property that we want the real line to obey. And that property is that if you have some subset of the real line that should have a boundary, i.e. it is bounded, so of course you can have some subsets that aren't going to ever have a boundary because they're unbounded. So if you, for instance, take the subset which is all of these integer points, of course that goes on forever in this direction and forever in this direction. Of course that's never going to have an edge. But if you have a subset that should have a boundary, so let's say it has an upper bound and it might have a lower bound as well, so if it's bounded by this element 5, so this element 5 is bigger than all the elements within this subset, so it's some subset over here, and maybe it has a lower bound as well, so -3 is smaller than or equal to all of the elements of this subset, so it's within here, i.e. it's contained, it's bounded. In that case, we want its actual least upper bound, and indeed its greatest lower bound, which is the same thing from the other side, to be defined. We want to be able to go right to the edge of the set and say truly where is its boundary, where is the edge of this set. And we do not want it to be the case that that barricade that you put at the edge of the set is actually an undefined point. It's a gap in your model of the real line. We want it to be the case that wherever you need to put one of these barricades for the edge of your set, that exists within your structure. Now the rationals doesn't obey this property, and let me show you an example of a subset of rational numbers that doesn't then have a least upper bound. So if we take our subset as follows, so elements that are within the rational numbers such that they are greater than 0, but also such that they are, when they are squared, the answer is less than 2. So if we look pictorially at what this is going to mean, so here is our line with the rational numbers now on here with their geometric meaning that we've discussed earlier. So this is going to be all of these rationals that are in this gap. So all of the rationals between 0 and 1 are going to be here. 0 itself isn't going to be in here. I've not yet let 0 be here. And then it's going to include some that are greater than 1 right up until we get to ones that when you square them are greater than 2. So all of these 1.1, 1.2, these rationals here such that when you square them the answer is less than 2, they're all going to be in here. Now this set does not have a least upper bound, and we'll show that rigorously in just a moment, but intuitively the reason it doesn't have a least upper bound is that the boundary point, it should have a boundary, it should have an edge, but that edge is going to be an element that squares to give 2, and that of course isn't within the rational numbers, so the edge of this subset is a hole in the rational numbers. It should exist, but it's a hole there. And this, therefore, this concept of least upper bound is helping us to capture exactly what we don't like about the rational numbers, that there are these holes, there are these subsets that should have edges, but which don't, because the edges are holes in the rational numbers. And then if we insist that that we want an ordered field that obeys this property, that's how we then have a better characterization of the real numbers, indeed the characterization of the real numbers, although we won't quite prove that in this video. We'll prove that in later videos in the playlist on real analysis. But here what we're going to do is characterize this property of the real numbers and understand why the one-dimensional continuum that we're trying to model is going to obey this least upper bound property, as it's called. So now let's properly prove that this set has no least upper bound in the rational numbers. So we'll do it by proof by contradiction. So let's assume then that there is a least upper bound for this set within the rational numbers. We'll call that least upper bound L. Now what do we know about L? Well, we know that whatever L is, it's a rational number, so when you square it, it cannot equal 2, because we know that there is no rational number that squared equals 2. So that means that either L squared is going to be greater than 2 or L squared is going to be less than 2. Now we're going to find problems with these two things. We're going to show how these two things can't be the case, otherwise it would contradict it being a least upper bound. So let's start off actually with L squared less than 2. I find this one slightly easier. So if L squared is less than 2, what we're going to show is that this contradicts L being an upper bound even. Because if we consider the number L plus some tiny little epsilon, so epsilon is some rational number, so we're going to consider L plus some tiny additional bit, and we're going to try and find a small enough epsilon such that if you do this and take L plus epsilon, that its squared is still less than 2, and that would then contradict L being an upper bound because we've got another element, L plus epsilon, that is still within this set, which is clearly bigger than L, so it would contradict it being an upper bound for this set. So if you consider what L plus epsilon squared is going to equal, it's going to equal L squared plus 2 epsilon L plus epsilon squared. So if this is going to still be less than 2, if we still want this to be in the set, we need this to be less than 2. So we can put this as less than 2 and then take the L squared to the other side. We get this difference, 2 epsilon L plus epsilon squared needs to be less than 2 minus L squared. The other way of seeing that is that this thing here is the same as L squared plus this little bit, this term, 2 epsilon L plus epsilon squared. So we need this to now be smaller than that gap between 2 and L squared, and that gap has size equal to 2 minus L squared, so we need this to be less than this. Now, how do we do this? Well, we use a trick that we use all the time in analysis. So actually, this is really important to get your head around because we'll use this trick at other points in analysis. So if we think about this epsilon, it's a rational number, it's going to be greater than 0. If we say, let's make it so that it's smaller than 1, then because it's greater than 0, we can multiply both sides of this inequality by epsilon and it must still be true. So multiplying both sides gives us that epsilon squared is less than epsilon. So this tells you the familiar fact that if you have a number between 0 and 1, then if you square it, its square is less than the number itself. So we're going to use that fact. So if we say we'll accept that epsilon has to be less than 1, after all, we want epsilon to be small, 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 so let's just take that curtailment, then we can say that epsilon squared is less than epsilon, and that allows us to say that this difference here, this 2 epsilon L plus epsilon squared, it is less, therefore, than 2 epsilon L plus just epsilon. So if we were to make this less than this, then this would be forced to be less than this. So now let's just try and make 2 epsilon L plus epsilon less than 2 minus L squared. And the reason that's useful is we can now factor out the epsilon and bring the 2L plus 1 down here. So we need to make epsilon less than this thing here. And this now is just in terms of L. There's no epsilon here. So whatever L you had, you can put it in here and you can get an epsilon. And I am saying to you that if you use that epsilon, if you consider what L plus that epsilon is equal to, that is now going to square to give something that's less than 2. And the other curtailment on epsilon is that it has to be less than 1 as well. So you need epsilon to be less than 1 and less than this. So just pick some rational number that's less than this, less than 1 as well. I guarantee you that that L plus epsilon, its squared, is going to be less than 2, and therefore it contradicts L being an upper bound because it's still within this set, but it is greater clearly than L. So this cannot be the case. If this were the case, it would contradict L being an upper bound. Let's now do a similar argument for this one. So for the possibility of L squared is greater than 2, a very similar argument, although we are going to need a little additional bit at the end. So the aim of what we're trying to do now is find a slightly smaller rational than L, an L minus epsilon, that is still going to be an upper bound, and that would then contradict L being the least upper bound. So we want an L minus epsilon such that when you square it, it's still going to be greater than 2. Expanding this, we get L squared minus 2 epsilon L plus epsilon squared is going to be greater than 2. So what we want is that this bit that we're taking away, so we're now looking at L squared minus this bit, so we've put brackets here, so we pull the minus out, so we get 2 epsilon L minus epsilon squared now. This is the bit we're subtracting off the L squared. We want it to be the case that this bit that we're subtracting off is smaller than the difference between L squared and 2, smaller than how much bigger L squared is than 2. So we want this bit to be less than L squared minus 2. Another way that you can see that is what we've done is taken this to this side and this to this side. So we want this to be the case. We want to pick an epsilon such that this is true. Now again, we're going to use our same trick that we applied here. If we assume that we'll pick epsilon such that it's less than 1, so we make that curtailment on epsilon, but that's not a big hindrance to us at all, then we know that epsilon squared is going to be less than epsilon. So therefore, it's enough to pick an epsilon such that this inequality holds true, because the instant this inequality holds true, this one will also hold true, because this is forced to be less than this. So if this is less than this of course is going to be less than this by transitivity. So we just need to pick an epsilon such that this is true, factor out the epsilon there, and we get that we need epsilon to be less than L squared minus 2 over 2L, and that shouldn't say minus epsilon, that should say minus 1. I'll just correct that. So there we go, nicely corrected now. So L is a rational number, so when you square it, you subtract 2 and then you divide it by 2L minus 1. You're still going to end up with a rational number here. So you now just need to pick another rational, epsilon, such that 1, it's less than 1, and 2, it's less than this. And if you find that, it will obey this property. Now, just to be ultra thorough, another curtailment on epsilon in both of these arguments was that epsilon was always assumed to be greater than 0. The whole arguments were on the basis that epsilon was a number greater than 0. So you might say, how are you sure that these fractions are going to be compatible with that? How do you know that this isn't telling us that epsilon needs to be less than minus 1, which of course would be incompatible? How do you therefore know that an epsilon is always going to exist? Well, my argument is quite simple. Just look at these things. Look at what is actually in these fractions. So in this one's case, L squared was less than 2, so 2 minus L squared was always going to be a positive number. Again, 1 is in this set here. L was going to be an upper bound for this set, so it was always going to be greater than or equal to every element of this set, so it was always going to be greater than 1. So again, 2L plus 1 was always going to be a positive number, so that's the proof that this was always going to be a positive number. In this one's case, likewise, L squared minus 2. In this case, L squared was going to be greater than 2. So this was always going to be a positive number. And 2L minus 1, again, same argument. L is greater than 1. So 2L minus 1 is always going to be greater than 0. It's always going to be a positive number. So both of these fractions are going to end up positive numbers. So it will always be possible to find an epsilon in both of these cases such that this holds true. So what we have shown now is that if this thing that we're assuming is going to be the least upper bound were to be greater than 2, it's always possible to find a smaller rational that is also greater than 2. What we now need to prove is that this other rational we found, this L minus epsilon, is still going to be an upper bound of this set, and therefore we've contradicted L squared being the least upper bound. So now what we want to show is that this L minus epsilon that we've found that obeys the property that when you square it it's greater than 2, that this is still an upper bound for our set S. So let's do this here. So we're going to rename, just for simplicity, we're going to rename L minus epsilon as Y. So we want to show that for all x within the set S, that they are all less than or equal to y. And what we know is that for all x in S, x squared is less than y squared. But we know that because all the elements in the set, their square is less than 2, and y squared we know is greater than 2. Therefore, we can say that for all x in S, x squared is less than y squared. So this is what we know, but what we want is that for all x, they are less than or equal to y. So how do we get from this to that? So quite simply, subtract y squared from both sides. You get x squared minus y squared is less than 0. You can then do some algebra, you can factor that out into x minus y times x plus y. And now what I claim is we can multiply through by the multiplicative inverse of x plus y. The reason we can do that is for all x in here, they are greater than 0. Y is certainly going to be greater than 1, because 1 is within this set, so y is also going to be greater than 0. So x plus y, therefore, is greater than 0. And if an element is greater than 0, its multiplicative inverse is also greater than 0. The reason that that is true is, imagine the opposite was true. Imagine that this suddenly was less than 0. So imagine this inequality was the other way round. Well, you could multiply both sides by x plus y, which is, we've said, greater than 0, and you'd then get that 1 is less than 0, which is nonsense. So it has to be the case, therefore, that it's this way around, the inequality, that the multiplicative inverse of an element that's greater than 0 is also greater than 0. So now, because this is greater than 0, we can then multiply this through by that, and we then get that this is x minus y is less than 0, and you can then just add y onto both sides to get that x is less than y. So for all x in this set, they are going to be less than this element because of the fact that for all elements in that set, their square is less than the square of this element. So what we have shown overall here is that this set, which is a subset of the rational numbers and which is bounded above, it has no least upper bound within the rational numbers, because what we have shown is that if it did have a least upper bound, that least upper bound cannot square to give 2, so it would either have to be the case that it squares to give something greater than 2, or it squares to give something less than 2, and we've shown that both of these possibilities cannot be the case, because if they were the case, you can always find a slightly different number, in this case slightly bigger number, in this case slightly smaller number, that contradicts it being either an upper bound or being the least upper bound. So this set has no least upper bound in the rational numbers. This is a very complicated, abstract way of capturing the fact that the rational numbers has no square root of 2. It has no edge for this set. Now, why have we taken something that was so simple and made it so complicated? Well, the reason is that this is obviously massively generalizable. This can be used for all the other numbers that are gaps in the real numbers. So, you know, the cube root of 2, the square root of 3, the square root of 5. We could find sets that are equivalent to these where their least upper bounds should be those numbers, but of course those numbers aren't in the rational numbers, so there is no least upper bound for those sets. There is no edge for those sets in the rational numbers. So that's the reason we've taken something that seems so simple and made it so complicated, because this idea of least upper bounds of sets is massively generalizable for all the different gaps, holes in the rational numbers. So now to define/characterize the real line then. So back to our original picture, remember we are trying to understand the one-dimensional continuum, one-dimensional reality. Now, some of you might get a little bit disappointed here because we are not, in this video, going to actually try and construct an abstract representation of every single point on the real line. We will do that in later videos in the playlist on real analysis. But now what we are going to do is characterize the real line. We're going to state properties that it is going to obey, and then we are going to infer incredible things in subsequent videos about the real line because of the fact that it obeys these properties. That is the spirit in which we are going to initially study the real line. We are not going to worry at the moment about constructing an abstract isomorphism of it. Abstract constructions of it are complicated, and it is complicated to understand how those abstract constructions are isomorphic to this intuitive concept that we are trying to capture of the one-dimensional continuum. So we will do those later. For now, we think of the real line as this true thing, this real thing, this one-dimensional continuum, the one-dimensional reality, which is the whole motivation for why we were trying to study this thing in the first place. That's what we think of it as. and we list the properties that it's going to obey, and then we can infer incredible things about this one-dimensional continuum, the one-dimensional reality, the real line, because we've worked out that it obeys these properties. So, property number one is that it's going to be an ordered field. Now, of course, it being an ordered field means that the rational numbers are a subfield of it, and the rational numbers are going to be along the real line, as we've already discussed. They're going to be in the same positions as we've already discussed. So at the moment, all I've put on are the two most important elements, 0 and 1, the additive and multiplicative identity. Addition then of two elements in the real line, so any two elements x, y, if you want to add them, the way that's going to work is you think of the arrow from 0, from the additive identity to each of the elements, and then you think of putting the two arrows end to end, and then the element that you arrive at on the real line, that's the answer as to what the two added together is equal to. And hopefully it's intuitively obvious. You can go through in your head the different axioms that addition needs to obey. Hopefully it's intuitively obvious that this geometric understanding of, or geometric definition of the addition is going to obey those axioms. Just to do a few, of course it's going to be closed, you're always going to get to another point on the real line. There is an additive identity, that's 0, because it's got the arrow of nothing, so when you add it onto another arrow you end up at the same point. It's going to be associative. I hope you can appreciate that. If you have 3 arrows added together, it doesn't matter whether you add these two together first or these two together first. It's going to have additive inverses because you just have the negative number, which is the arrow pointing in the opposite direction, which if you add it to, so if you take x for instance and you have minus x, if you add x's arrow to the arrow for negative x, it will get you back to the additive identity. And it's going to obey commutativity, again, because if you have 2 arrows and you're putting them end to end, it doesn't matter which way round you do it. Multiplication, again, we're going to define by this geometric meaning of it. So if you want to multiply by an element, let's say x, what that means is think of how much bigger the arrow from 0 to x is than the arrow from 0 to 1, and whatever the number is, or the point is, that you're multiplying by this point x, you want to stretch it out as much as you would have to stretch this arrow from 0 to 1 out to get to the arrow from 0 to x. Now, again, that's going to obey the axioms that we need it to obey to be a field. Let's just go through that. Of course, it's going to be closed. There is going to be a multiplicative identity. That's going to be this one element, because you don't need to stretch this arrow from 0 to 1 by anything to get it to 0 to 1. So if you multiply 1 by any element on our line, that element on the line is going to be fixed. Associativity is a little bit more difficult to see. Why is this stretching action going to be associative? Well, the answer to that is simple. When we stretch in this way, when we stretch our line in this way, this is actually a bijective map. Think of where all the points on the line are going to go when they're multiplied by a certain element, when they're stretched in this way. It's always going to be a stretch or potentially a flip in the opposite direction if we're multiplying by a negative number. So it's always going to be a bijective map. So if you're then doing multiple of these multiplications, you're just doing map after map after map, and you know that composition of maps is associative. So there's a good argument as to why this multiplication defined in this geometric way is going to obey associativity. It's clear that every element is going to have a multiplicative inverse, because if you look at, for instance, x, you can always find a element in here, so 1 over x is what we would call it, but that's just symbolic notation for it. You can always find an element in here where its ratio to 1 is the same as the ratio from 1 to x, so that when you multiply by it, it's going to be a shrinking down, and it's going to shrink everything down by exactly the opposite of what x is going to stretch everything out by. So hopefully again it's clear that there are going to be multiplicative inverses, apart from the element 0, on our real line. Commutativity is a little bit difficult to understand as well. Probably, again, the best way to think of this is to think of all of the multiplications as being these stretching maps. So if you think about timesing by 2 and then timesing by 3, so if you're going to times by 2, you're going to stretch the whole line out by a factor of 2, and then if you're going to multiply by 3, you're then going to stretch it all out again by a factor of 3 this time. And the answer you're going to get is going to be the same as if you firstly stretch it out by a factor of 3 and then take the answer to that and then stretch it out by a factor of 2. The amount that you've actually stretched, if you imagine the line being made of a fibre, the amount that that fibre is actually going to be stretched by is going to be the same. And there's the intuitive argument, or at least my intuitive argument, for why commutativity is going to hold in our real line defined like this. And then finally, distributivity. So this one's not difficult at all, but I've actually drawn a picture for this one because it's quite nice. It's an easy one to draw a picture for. So if we consider a plus b times c, so we have a plus b, our geometrical meaning of addition, and then if we consider stretching it all out by whatever c is, you can see that the answer that you get is going to be the same as if you firstly stretch a out by c and stretch b out by c and then add them together afterwards. So again, it's intuitively obvious that this geometric definition that I've given you of addition and multiplication is going to obey the axioms that is needed for field theory. And this is how I'm defining the real numbers. We're doing it by our intuitive understanding of it. We're not trying to create an abstract symbol structure for it. As I say, we'll do that in later videos in the playlist of real analysis. At the moment, we're saying the real line is this thing that we have intuitively, and we're going to say what properties we're going to have it obey. And so far, I've convinced you that it's got a geometric, it's got a notion of addition and multiplication that is very intuitive, that is going to obey the abstract axioms of field theory. Next, order properties. So our line has a really obvious order on it, the order in which the points appear here, where we'll say these ones are bigger than these ones. So obviously it has an order on it. That order is going to interact nicely with the field properties to make it an ordered field. So think of the two axioms that we need it to obey in order for it to be an ordered field. It needs to be the case that if you add an element onto both sides of the inequality, that the order is preserved, the inequality remains true. That is intuitively obvious. If you take any 2 points, let's think about x and y, and you imagine adding the same number onto both of them, that's just going to shift them along by an amount a. Of course, they're still going to be in the same order, so addition is going to be order preserving. Then think about multiplication by a number that's greater than 0. Well, that's just stretching everything out. You can again intuitively understand how that is going to be order preserving, so axiom number 2 of an ordered field is met. So intuitively, I hope I've convinced you that this line, this one-dimensional continuum with the geometric definition of addition and multiplication that I've given you, and the intuitive order on it, is going to obey the axioms of an ordered field. Now, the final axiom that separates it from the rational numbers. So the final axiom, or the final property that the real line is going to obey, is called the least upper bound property, or the least upper bound axiom. And this says that if you have any subset of the real numbers, so S, which is bounded above, so it has a number that is greater than or equal to all of the other elements, so an element on the line is greater than all the other elements within the set, then there must exist a least upper bound for that set, and we'll call that the supremum of the set S. So what this property, or this axiom, intuitively says is that if you have any subset, so consider this subset here, so these red dots are supposed to be points on our real line, and if that set is bounded above, so there is some element that is greater than or equal to every element in the set, then it should be possible to characterize the edge of that set. There should be a boundary of that set, an edge, and that edge should not be a hole in your structure as it could be in the rational numbers. The rational numbers did not obey this property. We saw that example of a set that didn't have a least upper bound. Its edge, its boundary, its supremum, its least upper bound was a hole in the rational numbers. So in our real line, we don't want edges that aren't defined. We don't want sets to be able to have edges that are holes in our structure. We want no holes. We want it to be complete, is a fancy word in maths. That is what this property is saying. That is what this axiom is insisting. It's saying that whenever a set should have an edge, a boundary, an upper boundary, an upper edge, that it does. It isn't the case that there's a hole there. And this property fixes the problem that we had previously where we had holes. We don't want holes in our real line. Now, just to point out that the moment you insist on the least upper bound property, you also get for free that there will be a greatest lower bound if the set is bounded below. So if the set is bounded below, meaning there's an element that's less than or equal to every element within the set, then there will exist a greatest lower bound if this property is true. The reason being that you can just consider the negative of this set. So you can take all of these elements times -1. You can take their additive inverses, so the symmetrical image of the set across the origin, and then you can apply this property. If it was bounded below in its original form, then now the symmetrical version of it is going to be bounded above, and therefore is going to have a least upper bound. And that least upper bound, when you reverse the symmetry, go back to this side, that will then be the greatest lower bound, the GLB. And the other word for that is the infimum of the set, or inf-s for short. So the moment you insist that any set that is bounded above has a least upper bound, has a supremum, you get instantly for free that any set that is bounded below must have a greatest lower bound, an infimum. So these are the properties that our real line is going to obey. It's going to obey ordered field properties, and it's also going to obey the least upper bound property. Together, we can call it a complete ordered field. So when you have an ordered field that obeys the least upper bound property, we call that a complete ordered field. So we are going to say that the real line is going to be a complete ordered field. Now, I hope it's intuitively obvious to you that this intuitive notion of the 1D continuum, which is what we are saying the real line is, I hope it's intuitively obvious that that should obey the least upper bound property. You should always be able to, for sets that should have an edge, you should be able to draw that edge, and that edge should exist within your structure. It shouldn't be a hole. That's what this is capturing, the fact that we don't want any holes to be able to exist in our structure. The whole of real analysis is now going to be about studying the real line, and we are going to be able to come to incredible conclusions about the real line. We will find out incredible things that happen in the real line, that are true in the real line, and they are going to follow from the fact that it obeys this axiom, the fact that it obeys the least upper bound property. And these incredible things are not going to be true in the field of rational numbers, despite the fact that it's still an ordered field. And they're not going to be true because the rationals don't obey the least upper bound property. So overall, to summarize this video, we have characterized the real line, not constructed it, but characterized it. We have seen how it has these geometrically defined addition and multiplication laws on it. We've seen how it has an ordering on it. We understand how the multiplication and the addition laws are going to interact nicely with the ordering. They're going to be order preserving, as long as in the case of the multiplication law, you're multiplying by an element that is to the right of 0, so a positive element. And we have said that it obeys this least upper bound property, and I hope you at least have some intuition as to why this one-dimensional continuum, the real line, should obey this property. We don't want it to have holes, and this stops it from having holes. Hopefully you intuitively have some understanding of why that should be true from the picture. We are now going to proceed in real analysis, and we're going to show incredible things follow about the real numbers once you have this characterization of it. Once you know that it obeys this property, then you can infer incredible things, and that's what we'll do for subsequent videos. Later in the playlist on real analysis, we will show that it is possible to abstractly construct a field that is ordered and obeys the least upper bound property. And what is more, we will show that any such construction that you make of a complete ordered field is isomorphic to this intuitive understanding that we have of the real line, the one-dimensional continuum, one-dimensional reality with the addition and multiplication laws that we have looked at. So there is only one complete ordered field. There aren't multiple of these. There's only one, and it is the real numbers. There's only one mathematical structure that obeys all of these axioms, and that is the real numbers. So we'll end it there. I hope you don't feel that I have pulled the wool over your eyes too much with this. This is a major, major property here. This is not trivial at all, and it is controversial. You know, there are some very prominent mathematicians on YouTube even that don't believe in this and denounce or would denounce what I have done in this video. So this is a major, major step, and I highly advise you to think and think and think about this. Remember, intuitively, what we are trying to do is construct or characterize the one-dimensional continuum, and I hope you agree with me in believing that the one-dimensional continuum should obey this property. So I've just added this addendum afterwards. I've kind of ruined my dramatic ending, but never mind. I just wanted to point out that in our new complete ordered field that is the real line, the square root of 2 is going to be an element. The reason being is that if you take this set, which is still a subset of the real line, because of the least upper bound property, it's forced now to have a least upper bound, which is going to be L, and L squared must equal 2. The reason being is it cannot be greater than 2 and it cannot be less than 2 for exactly the same arguments that we applied here. We proved it cannot be greater than 2, cannot be less than 2, and therefore if it's neither of those two things, the only option that's left is that L squared is equal to 2. So there you go, there is an element whose square is equal to 2. The square root of 2 exists in a complete ordered field. Thank you for watching. This is the true ending.